on Thanksgiving. Since I moved to New York University Abu Dhabi, sometimes my affiliation creates more questions than my actual talk. So let's clear the thing immediately where I am. So this is a map of Europe, and you see Abu Dhabi is where the pin is. Abu Dhabi is the capital city of the United Arab Emirates. And again, if I zoom a little bit, just to things that might be familiar, this is Qatar, or it might not be, the World Cup in 2022. This is Saudi Arabia, where women couldn't drive. And this is Abu Dhabi, where we have police women, among many other things. So this is a view of Abu Dhabi. It's a very nice place to come and visit. So I strongly encourage all of you to reach out to me if you want to have a break from the cold winter, when of course we'll be allowed to travel again. And in Abu Dhabi, there is a campus of the New York University. If you want to know why, that's a kind of a longer story. I'm happy to tell you later. It's an extremely international campus. As you see, we have 113 nationalities. We have 880 students per year. So we have about 3,000 students in total. And you see, we are split between male and female. And we cover almost all the subjects, both in arts and humanities and science. And it's kind of Babel because there are more than hundreds of languages spoken on campus, which makes teaching and research very interesting indeed. Okay, I think I cleared up this part, and let's go back to business. Do we need to move beyond cold dark matter? So let's start with a simple check of what we know about our cosmos, and I don't think I have to convince you that most of the energy matter content of the universe is actually dark. And it's split roughly 68% in dark energy and 27% in dark matter, which trumps baryons, atoms, by roughly 5-1. So the usually accepted model for dark matter has three properties. We assume dark matter has negligible thermal velocity at decoupling, so all the velocity is due to gravitational collapse. There is only gravitational interaction, so it's dark, and it's collisionless. Okay. Now the question is this model able to reproduce observations? Well, on large scales, we all know that it's extremely successful. This is a very old plot, 2004, it's more than 15 years now, but things haven't changed much. So what you have here is the power spectrum. So this is the power spectrum, and this is the wave number K. And what you see here, this red line, it's not a fit, it's what we think the model is. And then what you see here are all the data that go on top of this model. So the red line here is mainly obtained from cosmic ray background, and yet it's able to reproduce a large variety of observations on very different scales. Now, all the provenance usually come from small scales, as Paolo was hinting before. So there are two things here. The first one is that we can't really make predictions a priori on the structure of dark matter on small scales. Practically everything we know comes from numerical simulations. And as I say here, there's no a priori model for dark matter, but yeah, you should wait for Jenny's talk because she will challenge somehow this sentence. So the question is that why? Why numerical simulations? Why we cannot make a priori model for dark matter? Well, in cosmology, we are in a kind of lucky situation. We know the initial condition of our universe, which are given by the cosmic array background. So practically, we know the status of the density fluctuation, temperature fluctuation is the same thing, and there was a roughly 10 to the minus 5 of delta rho over rho at the time 400,000 years after the Big Bang. And now we have the final structure of the universe. And if we ask ourselves, what's the typical density contrast, for example, from a collapsed object and the background in the current universe, we see that the density contrast is now of order of 1 million. So a galaxy is usually 1 million times denser than the surrounding. And all of that happened in between 400,000 after the Big Bang and today. So there are 11 orders of magnitude grow in the structure. And we're all physicists, and we're all very used to orders of magnitude, but it's funny sometimes to visualize things. So if I take an ant and I grow its mass by 11 orders of magnitude, what do I get? Give you a few seconds to come up with your own guess. 11 orders of magnitude, the mass of an ant. Well, the answer is that you get an Airbus A380. Actually, you get 10 of them. Okay, that's how much the density fluctuation of the universe is growing. Another interesting thing is to look at the time scale. So if I rescale the age of the universe to 80 years, when was the CMB radiation emitted? I can see your brain spinning wheels. Well, it was emitted when the universe was roughly 1 day old, 22 hours to be precise. So it's true that we know the initial condition of the universe, but practically the challenge we have in numerical simulation is that we have a picture of 1 day old baby, and we are trying to guess how this baby is going to look at the age of 80. And remember that this baby is growing by 11 orders of magnitude. Okay, the end that turns into the airplanes. And that tells you why we need numerical cosmological simulations. Okay, this scanning in the range in mass, time, and evolution goes beyond anything we can do with paper and pen. Okay, how do we do those simulations? The idea is pretty simple. We have the initial condition of the universe, and what we do, we take a little patch of it and we recreate a distribution density which has the same statistical properties as the distribution in the CMB. And this thing is not to scale by any means, by the way. And then once we have this dark matter density, if we only care about dark matter, it's pretty easy. We just have to switch on gravity and let this distribution evolve. And now you see here what happens. This is a density plot, a logarithmic density plot. And you see that the tiny fluctuation, 10 to the minus 5, they grow under the influence of gravity, and they make the typical filamentary structure, the cosmic web that we all know. And at the crossing of the filaments, what you have, the formation of massive halos. Now, usually the problems of dark matter comes from small scale, so we are much more interested in looking at galaxies. So for galaxies, what we do, usually we do zooms. So the idea is that we take a little halo in our cosmological simulation and we rerun the simulation, putting now much more resolution on that specific halo. And that's what you see. What we see here, it's the evolution of a halo, which is roughly the mass of the Milky Way. And by increasing the resolution, we saw that what at the beginning was a blob, it's actually made of many substructures. Those substructures are continuously orbiting around the main object. They're merging with the main object until you have the formation of the final galaxy. This is a typical n-body simulation, dark matter only simulation. Only dark matter is at place, and we are kind of neglecting the influence baryons. For me, baryons is everything which is not dark matter. So gas, stars, everything is baryons. Okay, where are the cold dark matter issues? And now you might have heard many problems for the cold dark matter. Sometimes they go with the name Caspian core, missing satellites, too big to fail. But actually, all those problems are just different manifestations of one single issue. It's fact, as I say there. And the fact is that dark matter halos are self-similar. Okay? There is no scaling gravity. So when you run a structure in a cosmological simulation, you always get self-similar structures. What does it mean self-similar? It means the following. If I show you this picture, which again is a density map of the dark matter halo, you cannot tell me what you're looking at. This object could be a galaxy cluster, something which has the mass of 10 to the 14 in dark matter, 10 to the 14 solar masses, harbors 1,000 galaxies, and has the size of a couple of megaparsecs. It could be a group, similar to the group where we live, local group. Handful of galaxies, typical size, 500 kiloparsecs. It could actually host the Milky Way here in the center, and then have roughly 50 satellites around, or even it could be the dark matter of a dwarf galaxy, one of the faintest objects of the universe. And there is no way, by looking at this picture, you can tell me which one of 4 baryonic pictures you're looking at. That's a self-similarity. One way to express it in a more quantitative way is to look, for example, to the fact that if I plot the density of dark matter versus radius, all dark matter halos, they tend to follow the same universal profile. So dark matter is always distributed the same way as a function of radius. This is density versus radius. Since I want to compare with data, it's better to change mass and radius into velocity. Right? I can create the velocity by just simply doing square root of gm over r. And now what you see here, it's radius versus circular velocity. And here there are the velocity curves of roughly 100 eras, and they scan more than 4 orders of magnitude in dark matter mass. But the point is that I can collapse all those lines into a single line with a structure by simply rescaling the radius by the virial radius and the circular velocity by some circular velocity. That again is the self-similarity. So all lines collapse. Another way to see this is that there is also self-similarity in the structure in the satellites. You see that you have a central halo and you have many satellites. Now, the number of satellites, it's always the same when we scale to the mass of the host halo. So if I ask myself how many satellites there are with a mass between 1% and 10 to the minus 4 of the central object, the answer is always around 300. Regardless if you're looking at 10 to the 14 object, 10 to the 13, 12, 11, 10, 9, 8, 7, 6, and allow me to start here. And this is the main feature. Dark matter halos are self-similar. Where is the problem? Galaxies are not self-similar. That's where all the problems come from. So here what you see is rotation curves. So the points here with arrow bars are real data. And there are 4. This is from a paper by Oman in 2015. And you see that this is the best fit from dark matter, the powerful light. And you see that dark matter can only predict one shape for the rotation curve because of self-similarity. But you see that this is good for some galaxies. It's very bad from some others. So this galaxy has a very different shape than the one predicted from dark matter. The same problem is also in the satellites. If I look at the galaxy clusters, I can literally count 700 galaxies within its period radius. If I go to the Milky Way, I only see 50 satellites. More than an order of magnitude less, that's sometimes the missing satellite. Where in dark matter, I just told you, there is no difference. Okay? So if you want to save for dark matter, you have to break its self-similarity. It's as simple as that. The question is just how you do that. Well, there are 2 options. The first one is to bring a scale into the problem in, let me say, the dark sector. So for example, think about self-interacting dark matter. You bring a scale, it's the cross-section. Something which is popular those days is fuzzy dark matter. Those are extremely light particles, 10 to the minus 20 and below electron volt. And they have a de Broglie length due to quantum effects, which is interesting for astrophysical effects. So it's the order of a few tens to hundreds of parsecs. And again, you bring the scale into the problem. Or you can create an interaction in the dark sector. I myself have worked with interaction between dark matter and dark energy. But again, you have to bring the scale into the problem. Or as I usually say, you name it dark matter. Because I think there are more models than people working on that in the community of people trying to go beyond dark matter. But there's an elephant in the room. And the elephant in the room is that we don't observe dark matter, right? There is galaxy formation. We never observe dark matter. We always observe galaxies and we infer dark matter. So the question is that can galaxy formation do the job and allow me to stick with cold dark matter because of the breaking of the self-similarity? So before going into presenting the results, let me spend 2 minutes to present you the project I'm leading at NIHAO Abu Dhabi, which is called NIHAO. And it's a project aimed to simulate galaxies with baryons. So NIHAO is an acronym, stands for Numerical Investigation of 100 Astrophysical Objects, and it also means hello in Chinese. And this is a collaboration between NIHAO Abu Dhabi, the Max Planck, where I was before, and the Purple Mountain Observatory in China. And here's the list, partial list of the collaborators. So one slide on the simulation. So the idea of NIHAO was to run as many galaxies as we could. We started with 100 as a goal, now we have more than 170. And the idea is to have extremely high resolution, to be able to resolve the small scales and ask ourselves the question, are baryons able to break the self-similarity? And if yes, on which scales? So what you see here is just a promotional movie of our galaxy. This is like Milky Way-like galaxy. You only see the stars here. There's also gas and dark matter. So there's a razor-thin disk with a bulge, with an halo. You see some satellites. That's a list of all the physics which is implemented. I'm happy to give more information if needed, but I assume you're not that interesting. So we have pooling star formation. We have feedback from supernovae, from black holes. We have black hole formation, and so far, so on. The key point here is that our galaxy has very high resolution. So this is the same movie I showed you before of the formation of the dark matter halo. But now, since we are running with NIHAO, we also have, for the same dark matter, also stars and the gas component. So here you see the gas component, and it's color-coded. Red is hot gas, blue is cold gas. And here you see the stellar component. So that means at the same time, we can follow the formation of the dark side, the gaseous side, and the bright side, the stars. Okay? So that's the whole point of this set of simulations. And Again, I have here one more promotional picture. So what you see here, it's what we can do. On the left, you have real galaxies. On the right, you have our simulated galaxies. But one of the great points of NIHAO is that since we have more than 100 objects, we are able to practically capture all different morphologies. You see grand design spirals, you see topped disks, you see mergers, and so far, so on, right? Because if galaxies are not self-similar, you need statistics in order to capture the caveat. We cannot simulate galaxy formation from first principle. When I was talking about dark matter, it was very simple. I have my density, I switch on gravity, I know how gravity works, I know GR, I know Newton, there's no questions there. For galaxy formation, we cannot do that. And we have to make choices. For example, we have limited resolution. So when I talk about gas, the typical element, gas element I have, which I'm going to draw as a particle, has a mass of 10 to the 4 solar masses. Okay? That means that I have to make a choice when this gas is going to transform into a star. Usually we have threshold, like minimum temperature and maximum temperature and minimum density. And when those thresholds are crossed, so when the gas is cold and dense, we decide that part of it stays gas and part of it goes into stars. But again, since this mass is 10 to the 4, we form a stellar cluster. I'm going to call it stellar particle, but it's not a single star. It's roughly 5,000 suns. And then we assume the sum of the stars inside this cluster are going to be massive enough to explode the supernovae, and we have some supernova energy. The super energy, it goes back into the gas, and the gas, which was at some temperature and density, moves at some other temperature and density. Now, I want you to appreciate the following, but this is where things happen. This is a star-forming region, this is Orion Nebula. What you see here, a massive star just formed, and you see that the radiation pressure is steering apart this cloud here, which is the initial birth cloud. All this beautiful physics, it's encompassed in a single element in our simulation. Okay? So what does it mean? It means that the first thing we have to do is to validate the simulation. So if anybody comes to you and tells you, oh, I'm doing galaxy formation, the first thing you have to ask is that, can you reproduce observations? Because one great thing with galaxies, and then we have a plethora of observations to do. And that's where NIHAO does very well. So for example, this is a stellar mass, halo mass relation, which is kind of popular those days. So practically there are ways through lensing and satellite dynamics, abundance matching, to know that for a given stellar mass of a galaxy, what its halo mass should be. And we know the real galaxies, they live around this black line, which is sunscatter. And the blue points here, this is from the original NIHAO paper, are NIHAO galaxies. So NIHAO galaxies are able to reproduce this relation. It means that for a given dark matter mass, they have the right amount of stars. And then you can go deeper. So for example, there is a lot of scaling relation for galaxies. So galaxies, when they have the size, mass, rotation, velocity, those numbers are all correlated. So it's very important that your simulation is able to reproduce those correlations. Here, for example, is the Tully-Fisher relation you might have heard of. So this is a typical rotational velocity of the galaxy and its stellar mass. And what you see here in red are the observation, and in black are the NIHAO points. And you see NIHAO is able to get the 0 point, the slope, and the scatter of the relation. And same here, there is the relation between the mass in cold, the mass of the cold gas and the size of the disk. And again, NIHAO is able to get slope, 0 point, and scatter. So this means that NIHAO galaxies are very good galaxies from their visible part. And here's just a list of papers. This is not the last one, is NIHAO 25. They're all numbers, so very easy to find NIHAO papers. And they address different topics. So we have, some of them are purely on the baryon content, some of them are on the galactic structure, and the one I'm going to present today are the ones that look at the dark matter. Okay. So the point is that we can compare apples with apples. We have real galaxies and we have simulated galaxies. Let me go back to the breaking the self-similarity. So this is the plot I was showing before. We have a rotation curve observed. This is the blue line here, which is the same galaxy as the red points here. We just used two different data sets, but it's exactly the same galaxy. IC 2574. And here you see the best fit from dark matter. So what happens when we introduce galaxy formation? Okay, if we do not introduce galaxy formation, these are rotation curves that we get, dark matter only. And again, self-similarity. When we introduce galaxy formation, we get the gray line, which I'm now here going on top with the blue line to make it more visible. This line goes straight to the points. And now, the point is that I never aim to reproduce IC2574. I have 100 galaxies, and I can find one, actually few, that do reproduce 2574. And this is the whole point. So can we break the self-similarity? And the answer is yes. So this plot here shows the velocity rotation that you get in a simulation with baryons divided by the one you get without baryons. If galaxies will stay self-similar, all those lines will flatten up in a single line, right? That's the whole idea of the self-similarity. Now, what you see that on large scales, they are all similar because they're dominated by dark matter. But when you go on small scales, this is a fraction of the period radius. When you go on small scales, these lines, they open up. And that's exactly the breaking of self-similarity. And you see self-similarity is broken in both directions. Some galaxies, they have more rotation. Some galaxies, they have less rotation. Some galaxies, they have no change, right? And so far, so on. The point is that you don't have any more a single line. It opens up. Why does it happen? So in this movie, what you see is the assembly of the gas of one of those galaxies. The gas goes in, it gets cold, and then when it's cold, it makes stars. And when stars are made, there are supernova explosions. So this sort of fireworks you see, those are the supernova explosions. So what's happening here? Every time there's a supernova, the gas expands and then contracts again, expands and contracts. What does the dark matter see? What the dark matter sees, it's a time-varying gravitational potential because of the gas expansion and contraction. Now, what happens is that this expansion and contraction happens on time scales of few mega years, where the dynamical time scale, typical of the free fall time of a dark matter particle in the inner part of the region, it's of the order of 50 to 60 mega years. So what happens is that the dark matter sees this variation on a time which is way too short than its dynamical time, so it reacts in a non-adiabatic way. So when the gas goes out, the dark matter has to react expanding. When the gas comes back in, the dark matter has to react contracting. But this reaction is non-adiabatic. And as we all know, a non-adiabatic process is not reversible. So expansion, kick after kick, the dark matter is either globally pushed out or brought back in. Okay, it never goes back to the initial self-similar distribution. So this is what's happening to the dark matter. That's how we break the self-similarity. So let's go back to the usual concept of universal density profile, which is used very often by particle physicists to make predictions, for example, for annihilation sink coming from dark matter. So if you have a self-similar universe, so pure dark matter, all density profile have exactly the same slope. And one way to characterize them is to look at the logarithm slope, so the derivative of the profile in the inner region. And we know that, so if we take the limit for the radius that go to 0 of the density profile, it goes with some power of the radius, and this power is -1. That's a famous Navarro-Franken-White profile. So prediction for cold dark matter, they should have all the same slope. That's what happens in a universe with baryons. So you have here, again, alpha, you have here the mass of the halo. This red line would be the prediction from a pure cold dark matter universe. It's not exactly -1, because -1 is the asymptotic value, and you know the asymptotic values on average, and it has a little bit of a mass dependence, but it's practically flat. Where instead, this is what we measure in our simulation. Changing line as a function of mass and as a function of time. So there's no more universal profile. So this is a snapshot of redshift 0, where you can imagine that the dark matter halo, which is 10 to the 13 today, if I go back in time, its mass is it's lower. And so what we're seeing, and there are data in this paper, is that the galaxy tends, so the dark matter halo tends to follow this profile. So we have three regimes. We have a regime at low masses where it's practically the same as predicted from dark matter only. That makes sense. If I have a very low dark matter mass, I have very low stars, a very low supernova explosion, there's no change. Then we have a sort of a sweet spot where the effect of the baryons is maximum, and you see this alpha goes to 0, and for people that are familiar with that, that means a cold profile. Then what happens is that if I go to the right in the halo mass, I am increasing the gravitational potential. So at a given point, the baryons and the supernova explosions are not anymore able to move enough gas around to modify the dark matter. And so I reach this kind of mean. And now what you see that my points turn from blue to red, and that's because the blue points is where I have feedback from the black hole. So what happens is that around 10 to the 12 halo masses, we know that the black hole at the center of the galaxy starts to accrete mass at a very high rate. And so the black hole is also putting new energy to the system, much more energetically with supernovae. And again, it's sloshing the gas, and my dark matter profiles tend to go up. But the key point here is that there is no universal dark matter profile, not anymore when the galaxy formation is included. The other issue was about the satellites, right? I told you expect the same number of satellites. So here's just a snapshot of the number of satellites in 4 of our high-resolution galaxies. So here, the black line are the results for the Milky Way. Here, the gray line is the result for Andromeda. And now you see immediately the 2 galaxies, they have very similar mass, they have very large difference in the number of satellites. And that's, again, is another aspect of the broken self-similarity. And now you see, if I just put in 4 galaxies, I'm able to bracket both results. So I get the right number of satellites in luminous satellites. So this number of satellites is a function of the stellar mass in both as from observation. So what's happening here? So you can see at this movie. In this movie, you have on the left the dark matter, and on the right the stars. And now you can immediately appreciate by eye that there is much more substructure in the dark matter than in the stars. So if you squint your eyes, you can see that not all satellites in dark matter, they have a correspondent friend in stars. So if you're a big satellite, look at this guy, who's this guy here. Clearly you have a dark matter and a stellar counterpart. But look at here, all those little satellites, there is no counterpart in the stars. And the reason is that you need a minimum mass of dark matter in order to be able to make stars, because the gas has a given temperature, and this temperature prevents it from falling into very small dark matter halos. Not to mention that even if you are able to connect a little bit of gas, then you have the first supernova explosion, and those first supernova explosions are able to evacuate completely the gas from the dark matter. And so you only form a handful of stars, and that means that you should be very close to the Milky Way to be observed. So look at here now, if I can manage to stop both movies, the amount of substructure you have in dark matter and the amount of the lack of substructure you have in stars. Okay, this can be quantified, and in this plot you have the stellar mass versus the halo mass, and in red and yellow you have all satellites. They have both stellar mass and halo mass, and you see down in those lines, their color just refer on the distance of the satellite from the center. Those are the dark satellites. So those are the satellites from which you don't have any stellar contact. And this purple line is telling you the fraction of dark satellites. So if you have a mass of 10 to the 4 and higher, you are bound to make some stars. But as soon as the mass of the dark matter halo goes below 10 to the 10, the fraction of dark satellites increases quite strongly. And after almost 1 decade, 10 to the 9, only a handful, only a few % of the satellites are able to have stars. Okay. So self-similarity is broken. In fact, if I go back to my initial plot, I can tell you what this dark matter halo is. This dark matter halo has a mass of 10 to the 9, and that's a stellar counterpart. There are stars only in the center. Only the big guy is being able to form stars. All the rest of the substructure is dark. Okay? So this object is self-similar. If I show you this object, you cannot tell what the hell you're looking at. But as soon as I show you this is a dwarf galaxy. Right? It's an object which has practically only stars in the center. And in case there are more in these papers about those very tiny galaxies, those tiny galaxies are the perfect place to look for what I call naked dark matter. Because in a tiny galaxy like this, the dark matter properties are the same as you would have without baryons. So you can neglect the effect of baryons in this very little galaxy. So usually I always get this question, how unique are those predictions? Right? Because those are my predictions. What happens if someone else comes tomorrow and gives another talk? Because I told you have to make choices. Well, those predictions are not unique. So you are right to be skeptical. For example, they strongly depend on the density we choose to make stars. So this density It's expressed here as a function of particle per cubic centimeter. So 10, it means you have to form stars, you need 10 particles per cubic centimeters. And I can allow to make stars at different thresholds. And now what you have is those points are rotation curves from dwarf galaxies. And the lines are the results from our simulations. So this is dark matter only simulation. You see the lines are all above the points. Even if you don't understand the axis, it's very easy visually. You want the lines theory to go to the points data. And in dark matter only, you fail. And now you see that if I change my threshold, I can either, let's say, save cold dark matter. So I can get here simulation when the line goes to the point. Or I can fail to save cold dark matter. So, since the predictions are not unique, but this is not true because we are talking about galaxies. So if I change any of my galactic parameters, I'm going to change a lot of visible prediction of my galaxy. So I don't have the freedom to choose those numbers. I cannot. For example, let's see what happens if I change my density for star formation from 10 to 0.1. What happens is that I'm changing the position of where new stars form. So what you see here on the background, it's a gas map of the galaxy. And these white points are the position of young stars. Now, if I have a very loose requirement to make stars, I can make stars everywhere through the disk, right? Because I need a low threshold. If I go here and I ask a much higher threshold, it's much harder to make stars. That means I can only make stars in two places, on the spiral arms and in the center of the galaxy. Right? That's the position of newly formed stars. But now you see immediately that the distribution here is very different from the distribution there. And one can do a very simple thing, just compute the power spectrum of the distribution. And that's what we do, what people did from this survey, Legas. And here you have the correlation length versus the clustering length. So the idea is very simple. You go to a galaxy and you look at the power spectrum of the distribution of young stars. And now you see those are what the observations are, and those are the values that I use for the threshold. So I cannot use a threshold of 0.1, because if I use a threshold of 0.1, I cannot reproduce the clustering of young stars. And the threshold n equal 10 or 20, actually we also try 50 and 100, they all end up in the same place. Those thresholds, which are the ones I need to break the self-similarity, are the ones that also reproduce observational data. So are there parameters? Yes. Do we have the freedom to choose them? No. Okay. So those people ask me how many parameters I have in the simulation, and I have to explain I have order 10. But those parameters cannot be set arbitrarily to reproduce a given property of the dark matter, right? Because they need first and foremost to reproduce the property of the visible galaxy. So the prediction from galaxy formation are quite robust, and they become extremely robust if you bring in more and more observations. And we have a plethora of observations on galaxies. So yes, there are parameters, but there are many more observables than parameters to constrain them. So that brings me to my partial conclusion. That means there are two more slides after this one. I think I can say that there is no observational evidence forcing us to move away from a simple cold dark matter. Cold dark matter plus galaxy formation is able to reproduce all current observations. Okay, and that's a fact. So it's cold dark matter than the answer. From the point of view of galaxy formation, no. Because as of today, there's no indication that we need a WIMP-like particle, something with a mass around GeV or higher. Any dark matter particle which is, say, not too warm does exactly the same job of cold dark matter. So to reproduce all the observations I told you so far, you just need a particle which has a mass, and here I'm trying to be quite relaxed in my boundary, above 10 keV. For a thermal candidate. So if you like stereometry and it's equivalent to 8 keV thermal candidate, this is perfectly fine. Which on the other hand is also a bit depressing because it's telling you that galaxy formation is not able to discriminate between 10 keV and GeV, TeV. Okay? So cold dark matter is not wrong, but this does not mean that it's right. Thank you.
Thanks, Andrea. Do you have any question for Andrea?
So if I can ask, thanks a lot for the talk. So one question I have is, can you say which baryonic effects are the most important ones? So for example, you talked about the supernova and the black hole. So can you make a statement like if you include those two, you will get close to the observed galaxies, or like how many of the baryonic effects are important?
So it's a very good question. So what you need in order to reproduce observation is something that prevents 100% of the dust from falling into stars. And so you need some effects that bring energy into the system. These effects usually go under the big umbrella of feedback. And now what you can have is that you can have the two most important sources of feedback are supernova feedback and black hole feedback. So once you have those two, then you can mainly replicate all the observations you can think of. So supernova feedback and black hole feedback are the two most important effects. Now, if you have any other feedback that you like from cosmic rays or anything, you can add to the pile. But those are the two main drivers because they move the gas around, and dark matter only reacts to change of the gravitational potential.
Okay, thank you.
Another question?
If I can ask a question, is there any prospect for calculating the baryonic parameters?
You mean for first principle? Can you expand baryonic parameters?
Yeah, so to calculate in some first principles way the effective parameters you put into your simulations to account for baryonic effects?
The answer is no. And it's because all those effects, they happen on, they're mainly led by thermodynamics and electromagnetism that happen on scales that are orders of magnitude below what we can resolve in the simulation. So the only thing we can do is to work with effective potentials. So we try to wrap all those effects on small scales under some guiding line. So the answer is no. There's no way we'll ever be able to calculate them from first principle. What we can keep doing is to get the information from simulation on smaller scales and bring them into our large scale simulation. But the short answer is no. And my camera isn't working anymore. I have no idea why. Happy to answer more questions.
Hi, may I ask a question?
Yeah, sure. Please go ahead.
Yeah. So thanks. First of all, thanks a lot for the nice talk. You put strong emphasis on the number of parameters and how well they are constrained by observations. You mentioned briefly that you have order 10 parameters, but they are not free parameters. So how many actually are free parameters that you can work around to match simulations?
So practically, all those parameters, they have some range that they move within. For example, we know what's the average energy per supernova, right? So I cannot use 10 to the 10 ergs. I cannot use 10 to the 100 ergs. Those parameters, they are constrained by physics. So what usually happens is that you choose one relation, for example, the stellar mass, halo mass, and you tune your parameter to reproduce this relation. And that's what we did. For example, we spent a lot of time to get galaxies around the Milky Way mass. You can see my screen, right? Yeah.
Yes, we can see your screen.
Thank you very much. Here, that are correct. And then you cannot change these parameters and you start changing the halo mass. And for example, we saw that we were able to reproduce also those galaxies. So each galaxy is done with exactly the same set of parameters. And then what we did, what you have to do, what everybody does, you choose the relations that you haven't tuned your parameter on, and you make sure you also reproduce them. Okay, so you use one relation, one set of relation for tuning, and then you check that you can reproduce relations that you haven't looked at. Okay, and those parameters, they move within some boundaries which are set by physics, as for example, the energy per supernova.
And this is enough to constrain all your parameters.
That's how we constrain our parameters. Yes, we have a range. We fix the number by using replicating one relation, and then we check that with the same parameters we can replicate many other relations, which are somehow related, right? Because here I'm fixing the halo mass and the stellar mass, but I can get the cold gas mass and the disk, the size of the disk in gas, right? Those numbers, those parameters, very far away from each other.
Okay, thanks.
Thanks. There are any other question for Andrea? Otherwise, I can ask one. Andrea, but you need information from the cooling function in this business. But these, you have other parameter there, no? That enters and matters, especially the composition of the gas.
This is all set consistently done in the sense we start with the gas which is just hydrogen and helium. Every time we produce stars, we pollute the gas when the stars explode the supernova, and all those yields of carbon, iron, you name it, they come from stellar physics.
Yeah, but you put a threshold on the density, no? So not larger than. So if the gas has a density higher than a given number, it just collapses and forms stars, right?
With some probability, but yes.
Okay, and this density is not very high.
So the observed one is around 10,000 particles per cubic centimeter, which is ridiculously low, right? I mean, the air we are really, it's Avogadro number, 10 to the 22, 10 to the 20 particles. This density we can reach in the simulation, it's around 100. And we saw that if you use 10, 50, 100, 200, 500, it converges. But yes, there are thresholds. But I show you that those thresholds, they have some other effects. And so you don't have the freedom to choose them. And once the elements are produced, then the supernova ejecta, they bring them all around the galaxies. We have diffusion, we have transport.
And then it's consistent, okay.
And we can reproduce the behavior of the metallicity mass relation. So how many metals is a chemical bond that we use they use in astronomy, actually. The periodic table for astrophysics is hydrogen, helium, metals, 3 elements. So metal for me is anything which is heavier than helium. And we can reproduce the abundance in galaxies as a function of values.
Okay. You didn't take into account the molecular hydrogen for the formation of the first stars, right? So you just cool at 10,000 Kelvin, not below. Exactly.
What we assume is that when it's dense enough, hydrogen cooling will start. Nature will do that for us. And so you will form formation of stars. You don't need to follow it directly because it's a runaway cascade process. So once you enter in the cascade, you know that you're going to form molecular hydrogen.
You form a big star, not the small one, no? So if I recall correctly.
We form a star cluster. So we only form a ball which contains, on average, 10 to the 4 stars. It depends a little bit on it.
I see. Okay.
And we have an initial mass function, so we know how many massive stars, how many low mass stars that are within our ball, so we can predict how many supernovae we expect. But everything is self-consistent, so you don't have the freedom to play around with those things.
Okay, thanks. I think that we can move to the